So I hope my screen is visible to all of you.
Yes, sir.
So today we again continue with CNN as we had started yesterday. Okay, now here today what we are going to do is how will a multi-channel convolution work. Now typically here what we wanted to say is something that, and then we are looking at the discrete case of this one. So say I have a image, a color image. Now a color image typically is represented by a 3-channel matrix. So you have number of rows, which is M, number of columns, which is N, and over here you have C number of channels. Okay. Now channels means how many such 2D tensors essentially make up how many 2D matrices make up this kind of a 3D tensor. So here I call this as my input X, and this X belongs to R power of C cross M cross N. So this is the typical convention which we use in our tensor representations for deep learning purposes, and it's just a matter of convenience whether you have your number of channels in the first index or you have your number of channels in the second index. But for our purpose, we are going to return to having this number of channels represented in the first index itself. Now, if I want to convolve this one, look into it. I would be needing again a 3D tensor itself in order to convolve, where the number of channels of this tensor is the same as M, same as what you have in X, which is equal to C. The width of this tensor is W, and of this one is H. Okay, now this convolution kernel, I will not be using W anymore. What can we use? Tell me some alphabet which we can use. I don't want to use this W again. Then it will lead to a confusion.
Sir, B.
What? B.
P.
P. Okay. P. Because the other one we typically use in systems theory is H, but again H will also get confused over there. So I have P, and now this P belongs to C cross H cross W. Okay. So now if I convolve between them, so let me say this is my input, this is convolution kernel, and now if I convolve this one, what am I supposed to get is the question. So this resultant over here will actually be a single channel thing. So Y, which is the resultant, so let me call that as an output, that output is a single channel, which is 1 cross OH cross OW. And then we can write down whatever is OH OW as OW. So now here let us see as to how this operation happens. So let me write down a simple matrix over there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is the first channel of X. Okay. And say that 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. This is my second channel of X. So essentially what I'm saying is that I have X, which is x1 comma x2. This concatenation thing happens over there. And then I write down my P. So say this is 101, 102, 103, 104. So this is equal to the first channel of P, and 201, 202, 203, 204. This is equal to my second channel of P. In that case, what will my first location look like? So my first location is going to be what I operate on this block of Y. So let us look into what is this first location of Y going to look like. This is my resultant, which is Y. One comma one location. So what will be the value over there? Can somebody tell me? What will be the value at y1 comma 1?
Uh, 204.
So how will you derive? So it will be 1 into 101 plus 2 into 102 plus 5 into 103 plus 6 into 104
Triple. So
plus
124.
hmm?
So 1444.
Let us do this one. Plus 10 into 201 plus 11 into 202 plus 14 into 203 plus 15 into 204. Now tell me, what is this value?
So won't we flip them?
No, so we are not doing so. This essentially is corresponding to that W star.
So 11,578.
11,578.
Yes, sir.
Okay. Now, similarly, for the next location, I will have it like this. So accordingly, so this goes my next location. So this next location is going to be y of, so I have a row column index. So it's my first row and second column. So what is my y of 1, 2 going to look like? What is this going to look like?
2 into 1 is 101.
2 into 101 plus
3
what?
into 100. 3 into 102.
102 plus
6 into 103.
hmm,
7 into 104.
hmm,
11 into 201. 12 into 202. 15 into 203 and 16 into 204.
no, wait, that was 15, right?
Yeah.
And this is equal to
12798.
hmm?
12798.
Okay. So like this, I can now obtain y1 comma 3, and then like this, it keeps on going. Okay, so on and so forth. And then essentially now I am able to create this output matrix y. Now, what will be my y equal to? So y not equal to, what does y belong to? So essentially I'm asking you, what is the size of y? So the size of y is, it will have one channel. Okay. Now it will have number of rows. So what is the number of rows which I have? So I have m minus h plus 1 cross n minus w plus 1. Okay. Now let me go to the fun with the convolutional neural network, what we have. So in order to implement CNN, we represented something like this. So you will not just be having one convolution kernel, but you will be having multiple such convolution kernel. So I have my standard input tensor, which is X. I can have multiple of those convolution kernels. Okay. Now, this I call as P1. This I call as P2. Like this, it keeps on going. This is my some P small k. And this goes up to P capital K kind of a thing. So that's the K number of such convolution kernels which I have. Now what I do is that I run this convolution operator. Over that. So I have X, C cross M cross N. And here each of these PKs belongs to the power of 1, C cross H cross W. Now together I can write this convolution kernel as P is equal to, so I can write this. This implies I can have P is equal to a concatenation of P1, P2, like this up to Pk, such that this belongs to R to the power of K cross C cross H cross W. Okay. Now I convolve, and in order to make it as a CNN, I will also have a bias which is getting added to each of them, and this is a scalar bias. Okay, so essentially all of these biases to me will also form a tensor B, which is equal to this concatenation of B1, B2 up to Bk, such that this belongs to R to the power of 1 cross K, or sorry, K cross 1 if I write it to K cross 1. Okay. Now essentially as a result of this, I'm going to get down one of these channels, which is Y1. Then I'm going to get down the next channel, which is Y2. Like this, it keeps on going up to the kth channel, which is Yk, and the final one, which is Y capital K. Okay. Now if I concatenate all of these, so my resultant Y is going to be a concatenation of all of this. So my Y is equal to concatenation of Y1, Y2, like this up to Yk, such that this will now belong to K cross OH cross OW. This is what we would be getting. So typically in a CNN, you would see that there are multiple such factors which are involved. One is that convolution kernel, which is a learnable layer. So let us mark each of them. So this solid filled box, this is learnable. Also, these biases, they are also learnable. These are the only learnable layers which you have in case of a standard CNN. For like all the X's and Y's, they are just inputs and outputs. So you don't have anything to change around in the parameter. They are not learnable blocks over there. So if I want to define a CNN in any case, in general, I will be able to write this CNN expression something like this. So I will be getting down Yk, which is equal to your X convolved with Pk plus Bk, and Y is equal to concatenation of all of these Y1, Y2 up to Yk. And here now I can write down that X belongs to R to the power of C cross M cross N. P, which is equal to again P1, P2, Pk belongs to r to the power of k cross c cross m cross n, sorry, k cross c cross h cross w. Your b, which is equal to again scalar b1, b2, bk, belongs to r power of k plus k cross 1, and y belongs to r power of k cross OH cross OW. Now this OH can again
Sir,
be derived. Yeah,
sir, K is the number of classes in the output section.
no, k is the number of convolution channels which I have, or convolution kernels.
Okay.
So look over here. So I had k number of convolution kernels.
Yes, sir.
Okay, so k is the number
Sir,
of convolution kernels. It's not about the number of classes or anything. We'll come to a full network construction where I will show you what is the relationship with the number of classes which you have.
Sir, here we
So
are adding
then-
bias to the output of convolution between X bar and P, right?
Tell me.
Here we are adding bias to the output of convolution between X and P, right?
Yes.
And the output of convolution between X and P is a three-dimensional tensor, right?
The output of convolution between X and P will not be a three-dimensional tensor. What did we get? It was one-dimensional.
Okay, yeah.
Why will it be a three-dimensional? So the way it will become three-dimensional is because you have multiple such convolution kernels. So each is giving you a two-dimensional tensor. Now you are going to concatenate all of these two-dimensional tensors in order to get this three-dimensional tensor.
Yes, sir. Yes, sir. Got it.
Sir, but when we convolute that x bar with the P1, we are getting a two-dimensional matrix, right?
Yeah, so this is what I'm saying.
Yes,
So
sir.
for
So,
every convolution kernel and every convolution operation, you have a two-dimensional.
yes, sir.
Now I
So,
have k such convolution, unique convolution kernels.
but then B1 will be added as a scalar to each point of that.
Yes.
matrix. Okay.
Yeah.
Okay.
So if I have a matrix and I have a scalar which is added, what does it mean? My operation, it will add the same value to every single
Yes,
element
yes.
of that matrix.
Yes, sir. Okay.
Sir,
Yes.
why are we using multiple P's in the convolution? Are they representing the weights for every class, or is it something else?
So every convolution kernel over here is similar to a separate neuron in a fully connected layer. In a fully connected layer, what did you have? So you had my inputs and I was connecting it to multiple outputs over there. So I have multiple such weight vectors which I was getting. Now, each weight vector corresponds to every single neuron over there. Now here I am not having a fully connected representation, but I have a linear time invariant or linear space invariant kind of a representation, which is achieved by using convolution. So every convolution kernel is what represents the weight corresponding to a convolutional neuron. Is that clear?
Yes, sir, but not fully clear.
So in a fully connected layer, what did you have?
So we have layers of neuron, the hidden layers, and the output layer.
So
And the
I'm just
input layer.
considering an input to output relationship. Okay.
Okay, sir.
So in my input, I have my X, and then okay, wait, let me draw and show it. So I will come back to this calculation, but let me first clear off this doubt. So in my fully connected layer, what did I have? I have this X1, X2, like this up to X, say, capital N. And I had this one as Y1, Y2 up to Y of capital M. Okay. And then I had these weight combinations over here. So what was I calling it? So Y1 is equal to x, this whole x into some w1 plus b1. Then y2 is equal to x into w2 plus b2. Like this I used to keep on going, and then I would get down ym is equal to x into wm plus dm. Okay. Now look into these parallels. What I am representing is, instead of this operation anymore being a product operation, so in CNN you represent this as x convolved with this p of k. So I'm just representing that a convolution. Now if I do that, then this one, which is weight of a perceptron, now here this becomes learnable, say weight or parameters of a CNN neuron, a convolutional neuron. Is this parallel clear to you?
Yes, sir. Sir, but here M represents the number of classes, right? And
no, M is
this,
not. I mean, for our simple cases, this may be number of classes, it may not be number of classes. So if this is number of classes, then here also your K will represent number of classes. But we did not build a complete network. We had built out only one layer. Remember that.
okay, sir. So then if we have multiple layers, then this whole operation will be like executed in sequence.
Yes.
Okay.
So for giving you an illustrative example, I had said like, okay, this will be equal to number of classes in case I just have one single layer. But in general purpose, I will not be having a single layer. So now let me get back to this one. So what is my OH?
Hello, sir.
Yes.
So just one small thing, like y is basically a 1D tensor, right? Like after the convolution is happening, y are a bunch of like 1D tensors, y1,
No.
y2, y.
No. Y is a 2D tensor. Look back over here.
Okay, sir. Okay. Sir, like, what do we mean when we say like when you say like we are concatenating them like to form the entire one?
You are concatenating them along the third dimension. So I'm stacking one behind the other.
Okay, so we are manually forming the third dimension by concatenating them.
Yeah.
Okay.
So is this called 2D CNN or 3D CNN?
This is a 2D CNN because the translation is in 2D. If the translation was in, so that dimension, whether it's a 1D, 2D or 3D is dependent on in how many dimensions is it translating. So here it translates only in the X and Y, the horizontal and vertical dimension. That's why it's a 2D CNN. In the third dimension, it cannot translate because the number of channels in the input and the number of channels in the kernel, they are the same.
So we can also have what is called as 3D CNN, right? When the number of channels are more than 3 or something like when you have more number of channels, we can have a 3-dimensional CNN also, right?
Yes. You can have a 3D CNN, 4D CNN, any order of CNNs.
Okay.
So we'll come to that. I mean, I'm going to be close to exactly how to see this into an extension. So this form of representation which I'm drawing over here, this will actually make it clear whether it's a 2D CNN, 1D CNN, 3D CNN or whatsoever. And this OH which you have over here, which is essentially the dimension along of the output along the horizontal direction. So what is OH going to be? OH is going to be M minus H plus 1 and you have OH is along the height or the vertical dimension, and then or the column, or basically rows. OW is along the columns. This is going to be N minus W plus 1. Okay. And what did I miss out? Yeah. So also you know that this Y is equal to this concatenation of Y1 up to Yk, and then that is what belongs to this R of K cross OH cross OW, and your each of Yk is what belongs to R of 1 cross OH cross OW. This is what you had. Okay, so now I just rearranged my slides a bit. So that parallel which I was drawing, I just moved it a bit forward so that we don't have confusion. Now here, if you look into this one, so I was looking into this like whether it's a 2D or a 3D or what order of a scene. Now look over here. I had a input which had C number of channels over here. I convolve it with a convolution kernel. As of now, I'm taking just one convolution kernel, which has C number of channels. I add a bias, and then out comes a 2D thing. Okay, so this is a 2D CNN. If I replicate this one, that I have multiple of them, then I can stack and get down a 3D. A 3D tensor on the output, but it will still be a 2D CNN. Now say that I have C number of channels over here, and in my convolution kernel, I have some PC number of channels such that, so this is my input, this is my convolution kernel PK. So what I'm saying is that X belongs to R power of C cross M cross N. Okay, and I have this PK, which belongs to R power of PC cross H cross W. Okay, and your PC is less than C. So you add a bias, and then on this output, you are going to get this thing, which is OC. Now, interestingly, you would see OC as a dimension, which you can directly find it. So OC is equal to C minus PC plus 1. Now you can actually draw a parallel of these ones. So when I was doing the 2D case, I got my dimension as what? So in the 2D, it was translating along the horizontal and vertical direction. So my dimension along the vertical direction or the dimension along the count of rows was basically number of rows in input minus number of rows in the convolutional kernel plus 1. Similarly, my number of columns in the output was equal to number of columns in input minus number of columns in the convolution kernel plus 1. Now from there, if I look into the number of channels case over here in case of a 3D CNN. So let me just write it down as 3D CNN. then I would see that my number of channels in my output is equal to number of channels in my input minus number of channels in my convolution kernel plus 1. So is this clear to all?
Yes, sir.
Hello, sir.
Yeah.
Sir, this B over here in second part, I think it should be a vector, right?
No,
Yeah.
B will still be a scalar. See, when we say bias, bias is always a scalar. Every single neuron will have one bias associated with it.
Okay, sir. So it will be added to every PC, the PK value, right?
Every scalar element in that convolutional tensor. Like as a result of that convolution, whichever tensor comes out, on every single scalar element of that tensor, you will add the same bias.
Okay, sir. And sir, one more question, sir.
Yeah.
As over here, somewhere I have read that this is called filter, right, sir? PK.
Yeah, PK is also called as a
So,
filter. It's
yes,
called
sir.
as a filter. It's called as a kernel,
Yes, sir.
whatever you call it.
So, yes, sir. So, where I have seen that this number of filters we are using, that will be the output channels.
So this is the 3D case. Look into this one. In a 2D case, what do you have? In case of a 2D convolution, where your output is a three-dimensional tensor. So your Y is the output of a 2D convolution. See, this is a 2D CNN. Let me write it down. So this is formal representation of a 2D CNN. So over here, what do you get? This is your output, which is a 3D tensor, where the number of channels in the output is the same as number of convolutional kernels. This is for a 2D CNN. Remember, in case of a 2D CNN, your output is going to be 3D, your input is also going to be 3D. Your convolution kernel will be a 4D tensor, because you have a stacking of multiple such 3D convolutional kernels over here. Now here in the next slide, what we wrote down is a 3D CNN. So this is a snapshot of a 3D CNN. So if I want to write down the full operation of a 3D CNN, then it is going to look something like this. So in case of a 3D CNN, formal, wait, let me write operations in a 3D CNN. So you will have your input over here, which can be a 3D tensor. It can also be a 4D tensor. Okay. So typically it's actually a 4D tensor which you do over here. So how can I write it down? Wait, because you'll also have multi-channels over there in one. So this is my X. Now X belongs to a number of channels which is C cross the depth which is D cross M cross N. So this dimension is C, which is the number of channels which is present over here. This is my dimension of M. This is my dimension of N. This is my dimension of D. Okay, and this together is what I call as X. Now I can have similarly another such group of convolutional tensors. This one, which I called as P1, I can similarly have P2, and like this up to Pk. Now I run a convolution on this. I add a bias and out comes to me another 3D tensor. I run a convolution on this. I add a bias and out comes another 3D tensor. So this to me is y1. This is y2. This is yk. Okay. Now, what is this P? So this P is now a concatenation of all of this P1 to Pk. As a result of which this P has, so how many such kernels are there? K. Now each will have C number of channels, which is the same. So this is my dimension along channels. Now they will have a different depth. So say they will have a depth of D cross H cross W. So this is what I will have in this P. Now this Y over here is also going to be a concatenation of all of this Y1 up to Yk. So let us take it forward and now write down the formal representation of a 3D CNN. So in case of a 3D CNN, what do you write down? So in a similar way, you will write Yk is equal to X convolved with Pk plus Bk, and your Y is equal to concatenation of Y1 up to Yk. Now here your X being a three-dimensional tensor, this belongs to C cross D cross M cross N. C is the number of channels in that three-dimensional tensor. Okay. Now you will have your each Pk, which belongs to R to the power of similarly C cross small d cross H cross W. Scalar bias. And your P, which is equal to P1 concatenated up to Pk, which essentially belongs to R power of K, which is the number of convolutional kernels you have cross C, cross D, cross H, cross W. Now your y, each of yk belongs to r power of what? 1 cross OD cross OM, OD cross OH cross OW, and your y, which is equal to that concatenation thing. So this y over here, this belongs to r power of k cross OD cross OH cross OW. Now your bias is still going to be the same. So B is equal to all of this concatenation of B1 up to BK, which is equal to which belongs to R power of K cross 1. And your OD in the general case is going to be D minus D plus 1. OH is equal to M minus H plus 1. OW is equal to N minus W plus 1. So is that clear for you?
Hello.
Yes.
Yes, sir. So most of the things are clear. So, like here, can we say that that input is a 4-dimensional? So we can assume that it is a of a color images, right, sir?
Yes.
So here we can say that we can assume that D is the number of channels of a particular color image.
No. D is the time step.
Okay. And
C
is the
number of channels. So C is the red channel, green channel, blue channel. So if I'm just looking at the red channel across multiple timestamps.
Okay, sir. So while convolving it, so we will be taking all the red channels and doing
Convolving along the time dimension also.
Okay, sir.
But I'm not taking a channel by channel convolution. I'm taking all the 3 channels and convolving together.
Yes, sir. Okay, sir. So like, is there any like a useful thing where like our timestamp is coming before that channel? Like we have bunched out the time, a particular timestamp.
So you mean to say that if C and D get exchanged, which is like
Yes, sir.
I want to have my channels along the timestamp. I am not aware of any such thing. Generally, like the channel, see the concept of channel is an independent vector of all of them. But along the timestamp, I will not have independence. Along the timestamp, it's somewhat dependent. I mean, if I'm looking at a video, an object is moving. It is moving. So in time, there would be some correlation.
Yes, sir.
But color of an object is independent of each other.
Yes, sir.
So that's the reason. And a lot of this actually gets used in magnetic resonance analysis, where you have a real multi-channel thing. So that C can be something like 5, 6, 11, 13 or something of that order.
Okay, sir. Got it, sir. Got it. Thank you.
So, sir, if we are evaluating a video, then we have to evaluate over timestamp over each color.
Yes.
Okay, sir.
So you have these application examples. Don't worry. We are just learning like how this operation and tensor. So see these formal representations. What I'm teaching you in classes. A lot of times people have confusions. Once you start writing, say you're writing a paper, you are writing some algorithm, you're documenting it out. If you give it in this form, see this is so simple to understand. You know exactly what is the dimension of the things. What should the tensor look like? And what is the constituent, whether it's real valued, it's integer, it's positive real valued or whatsoever. Everything is very clear over here.
But isn't it odd, sir? We should be like, we should be evaluating color images over time, right? Like
you are evaluating color images over time only. So what is the dimension of your convolution? Your convolution kernel, what is it translating across? So this convolution kernel is translating across D. This D is your time. In case
Yes, sir.
of
Yes,
D.
sir. That I know. But you are saying that we will evaluate over each color. Like
When I say over each color, what do I see? So I have a okay, let me go back. So
I was saying,
see, this is for one color channel, this is for another color channel, this is for the other color channel. But here I have this dimension which is D, which is exactly my time step, which is matching with this D, which is my time step. This small block is going to convolve over this one, which is one of my color channels. So this one matches with this one. This one convolves with this one. This one does it with this one. But for each of them, you have this dimension, which is the time dimension, and this is the time dimension over here.
okay, sir.
We'll come to the video example when it will become much more clear. As of now, and yeah, it becomes hard to relate it. For me, I've been doing this in and out for so many years that it's very clear in my mind. But we will come to the video example and I will show you exactly like why that is packed in that particular way. But we are still left. I mean, I still have to teach you padding, stride, and then other non-linearities on top of it. We haven't yet touched upon that.
Yeah, sir. I was feeling good. Well, like we are in CNN and we haven't touched non-linearity yet.
No. The point is, until and unless you understand this basic operation of how the tensors of a single layer's output is going to look like, what will you do with non-linearities? People get confused at this stage. The reason I want you to understand this one very good is if your code is behaving erratic, how will you know how to debug it? This is the way how we know exactly like where the problem is inside a code if we wrote it somewhere wrong.
Yes, sir. Yes.
Okay, then we again catch up tomorrow. Tomorrow I'm going to start with stride, padding, non-linearities and actually draw a complete CNN. And then we will again represent this every single layer as a formal representation over there and see how it looks like.
Okay, sir. Thank you.
Okay, see you guys then. Bye.
Yes, sir. Bye, sir.
Thank you, sir.